Hello viewers, welcome to my channel KK Concepts of Electrical Engineering.
Dynamically induced EMF. Let us consider a uniform magnetic field. The flux density B is constant magnitude and it is time invariant. Let a conductor of length L be moved in the magnetic field at right angles to the field with a velocity V. As the conductor moves, it cuts across the magnetic flux, and as a consequence of this, an EMF is induced in the conductor. The direction of the induced EMF is normal to both the field and the direction of motion. The magnitude is given by E is equals to minus B L V in volts. The EMF is termed as dynamically induced EMF or motional EMF. Considering uniform or constant flux B, and it is uniform and time invariant. Placing conductor of length L, and I am moving this with the velocity V in this direction. Whenever this conductor comes into the field, it's going to cut the magnetic flux. That is going to induce EMF and this conductor. That EMF is given by this. Assume that the conductor is moved in the field at right angles to both field and velocity. So let this conductor is moved dx distance in time of dt. EMF E is given by d phi by dt from previous video. In this case, flux cut in time dt is given by flux density multiplied by area swept in time dt, that is given by B multiplied by L dx. The total length is L and dx is the distance is traveled. We need to find out d phi by dt, that equals to B L dx by dt. Now this dx by dt is nothing but distance per time, which is nothing but a velocity in this case. So I'm writing this as B L and velocity V. Dynamically induced EMF or motional E.M.F is equals to E motional equals to minus d phi by dt, which equals to minus BLV in volts. Direction is normal to B and V given by Fleming's right hand rule. Motion of a conductor in non-uniform time varying magnetic field. We know that F equals to Q V cross B, where F is the force on charge Q moving through the magnetic field of flux density B with the velocity V. Then from which F by Q equals to V cross B, where force per charge motional electrical field intensity and represented with the letter E M. E M equals to V cross P. Previous video we have seen that induced EMF E equals to closed line integral E dot dl, and this is motional electric field intensity that equals to, I'm substituting the value of EM here, then closed integral V cross B of dl. I'm having flux lines like this. Let it be. Let this be a conductor. If it is moving like this, then it's going to cut the magnetic flux. Then induced EMF is going to be there in the conductor. If it moves parallel to this, then there is no chance of cutting the magnetic flux. So there is no induced EMF. One is equals to length to 0 VB dx, which equals to minus BL V. For a conductor moving in constant uniform magnetic field, a motional electric field intensity EM may be attributed to every moving portion of the conductor. So the total EMF equals to E, that equals to EDL, which is again motional EMF EM, that equals to closed V cross B dot dl. If the magnetic flux density is also changing with the time, then in addition to the motional EMF, there is transformer EMF. We have seen in the previous class that E equals to minus surface integral of dB by dt of ds. Now, taking that into the account, the total EMF induced is equals to E equals to closed surface E dot dl to EMF due to uniform magnetic field, that is V cross B dl, minus the second term, that time varying magnetic field dB by dt of ds in the surface.
If you have any suggestions and queries, please mention in the comments. If you like this video, please like, share and subscribe. Thank you for watching the video. Please stay tuned for more videos.